And this is what we show the engineers. We sometimes do it post-mission. Sometimes we'll actually do it in real time. With about a 10-minute delay, we can deliver to the internet anywhere in the world this kind of display of what's going on in their well. 3 weeks ago, my chief geophysicist was in Chengdu, China, sitting next to the chief engineer of Anadarko. We were fracking a well in the Eagleford, in South Texas, at that time. And my geophysicist said, "Would you like to see your well and how the fracking's going?" He pulled out his BlackBerry, logged in, and watched a movie just like this. And the other thing to note, we're not getting more than 500 feet above any one of those wells, or below for that matter. The oil companies don't want to frack shallow. They don't want to spend time and money and energy fracking rock that isn't going to deliver hydrocarbons. Sir?
Doesn't that represent a lot of redundancy?
There is a fair amount of redundancy there. You're absolutely right. Although if you scaled those balls back to some real size, there wouldn't be as much redundancy as you might expect. The hydrocarbons only come out of the fracture faces. So we want to create as much complexity and intersecting fractures as we possibly can.
Talk to us about the one well that didn't go consistently with the other 6.
These guys?
Yeah, that's right.
Drilled into a shallower horizon?
Yeah, do you know what it is?
I don't. And if I did, I couldn't tell you.
You mean you couldn't or would?
Probably each. No, it was drilled. They are testing different horizons above and below to see whether they can get hydrocarbons out of them. But I probably wouldn't say any more than that, Terry. Ask Ray. So the issue here, to the seismologists in the audience, you will recognize that what we are dealing with is a signal-to-noise problem, particularly when we're working from the surface, which is the technology that we brought to the marketplace. So just how small are these signals? I'm going to show you an example from the Eagleford, but let me preface this by saying that most of the signals that we see, that we're able to detect from the surface, are on the magnitude scale that is typically quoted for earthquakes, are in the range of -1 or below. And I would say the average is close to -2, the detectable average. Obviously, there is a continuum of events that get ever smaller. -2. So Mark Zoback from Stanford, and they know a lot about earthquakes over there, told me that a -2 earthquake, to put it into perspective, releases the amount of energy that's about equal to taking a can of pop and dropping it from your waist onto a cement floor. That's the amount of energy that gets released. Clearly not something that we need to worry about as going to cause any damage on the surface. So we're down in the Eagleford, the Edwards Reef Trend up here, and down in South Texas, Duval, Live Oak County. And I'm going to just show you what some of these events look like when we have a surface array. Now these represent different lines of a surface array that have been put out around a well that's being treated in the Eagleford at around 7,000 to 8,000 feet deep. And the biggest event we saw actually had a local magnitude of about 0.8. That's a biggie. And we can see it with this. Now, here's our cumulative frequency diagram of where the events are. And down here is about -2. That's our detection limit from the surface. These events keep getting smaller. That event, the biggest we saw, has a motion at the ground surface of about 3,000 nanometers per second. That's the velocity of them. It's a pretty small motion. Here's a more typical event. It's event number 100 by the signal to noise, and you can see what it looks like. Here's down event 250, event 1000. When we're down in this range, the motion at the surface of the Earth is on the order of 300 nanometers per second. That's the velocity that we're catching in our velocity phones. And when we get down here, we're in the range of 10 nanometers per second. So that's our signal, anywhere from 10 to 3,000 nanometers per second into our phones. How big is the noise? Well, here's an example, not from the Eagleford, but from the Haynesville. A frac star put out on the surface. These are the lines that you were looking at before. And the average noise RMS over a 24-hour period, anywhere from In the blues, below 20 nanometers per second up to 200 nanometers per second. So clearly, the noise in a lot of our data is as large or larger than the signal on any individual phone. But then that's why we stack data in seismic, right? And we do have one other thing, one other tool that we can use, one other tactic we can use besides fold to overcome signal to noise. And that is, we have increasingly gone to burying geophones below the free surface of the Earth in order to get away from that very noisy environment. A lot of the cultural noise is largely confined to that free surface, or bound at least to the weathering layer. So if we go down, in this case, 100 feet, we can see that the average noise has dropped off down here into the 60 nanometers per second range. And if we go down 150 feet, a little bit more perhaps, 200 feet, and this is the phenomena we find. We find that that noise from the free surface drops off very quickly and then tends to flatten out. I'm going to talk a little bit about buried arrays in a minute, but I will tell you that typically what we do is a test to find out where that sweet spot is for putting these buried arrays, and that's where we'll put them. That helps us increase our signal to noise and consequently use fewer phones, lower fold, to achieve the same sort of resolution in our data. These signals are also, the noise is oftentimes at a little bit of a different band than our signal. And here's an illustration. Those are the spectra of the signals you were just looking at in terms of different depths. And here is the idealized spectrum of a -2 event from a reservoir depth as it would occur at the surface of the Earth. And now you can see, of course, this is per hertz or root hertz. You can see and it's in microns, so that's 1 nanometer per second, and that's 10 nanometers per second. But you can see that there's an opportunity by filtering out these low frequencies to perhaps get to a point where the signal to noise, even on an individual station, is 1-to-1. So it's a signal to noise problem that, particularly when we are working from the surface, is a very dicey one, since the signal is often an order of magnitude bigger. The noise is often an order of magnitude bigger than the signal that we're trying to capture. So how then has this problem of locating these small signals, these small microseismic events, typically been attacked by the industry and by academia? The legacy technique is to use the same technology that has been used and is still used to locate earthquakes. That is, to time the arrival of the P phase and the S phase of the signal, take the time difference, use some calculation based on that time difference to calculate or estimate a length, an arc length, to the hypocenter. Do a hodogram of the amplitudes on 3 axes, in other words, calculate the tilt of the wave field, and use that tilt to then give you a vector direction back to the hypocenter, and from that make some estimate of where the hypocenter is. That technique requires picking the P and the S arrivals very accurately. And since these events are pop cans hitting cement floors, you can't do that very easily from the surface. So the way that people approached that originally was to take downhole geophones, put them on a wireline device, and drop it down close to the reservoir. And that still accounts today for about 50% of the microseismic monitoring that is done on hydraulic fracturing. So you have these geophones, you treat each one as an independent station, you make an estimate of the hypocenter location from each geophone, and then you do some kind of a weighted average as to where the estimate of that particular event came from. There are some hair on this technique. Number one, it requires a monitor well properly positioned with respect to the treatment well. You can't do it in the treatment well itself. That's too violent an environment. That's expensive, and engineers don't care much for you sticking stuff down their wells unless it's going to help them produce more. Also, you can imagine from a geometric perspective that this aperture becomes vanishingly small as the distance to the event becomes larger. And typically we are limited to a distance from the monitor well about 3 to 5 times the aperture that you have in your individual monitor well, the aperture being the distance from the top to the bottom sensing geophone. Thirdly, if you have some systematic error that you don't take account for example, if this well has a 1 degree tilt and you haven't actually done a gyro down it and taken that into account, you may assume that the well is here when the well, in fact, and over 7,000 to 8,000 feet, 1 degree is quite a distance, whereas in fact the well is over here, and all of your calculations will put the event relatively in the right place compared to each other calculation, but absolutely in the wrong location. Happens all the time. So there's hair on this technique. That's kind of where we had the opportunity to come in and start saying, well, these small signals can be picked up by stacking, just like we do with conventional 3D data. We put pictures of antennas and all the rest of it, but that ain't for you guys. You guys can say 3D seismic, 2D seismic. We've been doing this for decades. We know that when we stack the data, we overcome noise and we can detect small signals. So here, in fact, is just an example. I was indicated earlier that we can take this random data and even before stack, we can cut out some of the noise by filtering. Here's an example of a raw record that we've then filtered back, and here you're starting to see the calibration shot peek out. And now if we add in the concept of stacking, just to calibrate you, here are a series of signals, a magnitude -2 signal in the raw, and that's about 10, 15 nanometers per second. A magnitude -2.5, a magnitude 3. And here, just for comparison, is the size of a signal that is equivalent to about a 1 pound dynamite charge that's been set off at the surface, gone down 10,000 feet with typical Q, come back up 10,000 feet, and that would be the ground motion at the surface, slightly bigger than a -3. Now, nobody questions whether or not we can do seismic exploration with a pound of dynamite. We do it all the time. So the point here is just that a pound of dynamite gives you a signal back at the surface about equal to what a -3 event is going off at that 10,000 feet. We added synthetic noise and then we stacked it with 1,000 stations typical of a frac star, and here you can see our little events. And down about -3, that's probably the detection limit of a surface array with 1,000 geophones on it. So this is just standard seismic work as far as I'm concerned. Here's an example then of how this progresses through the processing, through the whole process. We have 2 arms of a frac star, raw data, filtered data, I should say. It's not entirely raw. It's also been gained with an AGC of about 1,000 milliseconds in length. We have a string shot. We always set off a string shot in the well to calibrate our velocity model in order to get the absolute depth correct. We do that with downhole or with surface arrays. The velocity models that you get from conventional seismic data or from wireline data from the sonic logs need to have that calibration step in order to put things at the right depth.